First of all, thank you all for joining me today. We're going to discuss our new feature for calibration that was released with TreeAge Pro 2020. There are a bunch of other features included in 2020 that you can see here. If you're ever wondering what's come in new, you can always go to this section 1.4 of the help, and it not only has all the new features or enhancements, but if you click on the links, it will bring you to the sections that describe it in detail. But today we're just going to talk about calibration itself. So let's go ahead and get started with that. Any of you who have built models before, you know there are some challenges. There are quite a few challenges in building models, but a major one, and they're all related to trying to mirror true disease progression and treatment effects as accurately as possible. We are trying to make our models represent the true biology and physiology of these diseases and the impacts of treatment as close as we can to reality. And part of that challenge is creating the pathways that you see here in this model and the right health states for a Markoff model, et cetera. That's part of the challenge, but perhaps an equally big challenge is getting these probabilities right. These probabilities are hard, and oftentimes they're not fixed, although in this example I'll use fixed probabilities, but coming up with the right transition probabilities over time to represent true disease progression is a major challenge. And calibration isn't just going to solve that problem for you, but it's going to help. In other words, you have to start with some realistic values, and the calibration process is here to try to help you refine those values that you've already put in the model and make them as accurate as possible so that your outputs match observed data. So just at a high level, what we're doing is we're saying, okay, I've got my model, it's running, it works, but when I look at it against the observed data that I see on the output side, they don't match. And there's something slightly wrong with the model that I need to adjust to try to get that output data to match what I see in observed data. So that's what we're trying to do. So just before we start, we'll just start with this example model. It is right here on your software in the files view under example models, healthcare, calibration, Markoff. Now this model was introduced with the 2020 software. So if you still have old example models, you'll need to replace those. You can do that by, I'm not going to do this, you can delete this and then come over here to File, Projects, Recreate Tutorial Examples, and that will kind of refresh all these with the new models, including this calibration model, which is what we're using today. So this is a standard Markoff cancer progression model. I use this for illustrating different features and training all the time, just 3 states, background mortality, and then progression. And there are 4 key, let's just assume that the background mortality is perfect. This model has bogus background mortality, but imagine that came from the local authorities and it's perfect. So the question we're asking in this calibration question is, do we have the right probabilities here, here, and here? And in addition to that, the probability for progression is different for the 2 strategies. They're defined back here using cloning. So we actually have 4 probabilities, 2 progression probabilities, 1 death from local cancer, and another one, the 4th one is the death from metastases. And we're going to assume they're fixed, which is maybe not, for this example, it's fine. But they could be based on some kind of Weibull curve or something a little bit more complicated than just a fixed probability. So we have those 4 probabilities to work with, and we're trying to see if we can get our model to be more accurate and better represent the disease. So in order to do that, we have to have some observed data. So the assumption in this model is we have not all observed data out into the endpoint of every model output that's going to be generated. We have 4 sets of observed data in this hypothetical example that represent 5-year progression-free survival and 5-year overall survival for each of the 2 strategies. And we've collected that data and we've run our model, and we're basically saying they don't match. Now, let me address that a little bit more clearly here, or more quantitatively here. So what we're saying is what we're getting in the model is progression, and this is just the first strategy, but we do it for both. What our model is giving us is this for the 5-year progression-free survival, and it's giving us this for the overall survival. But what we saw in our observed data is this. Now, before I skip forward, I want to say, well, how would you know this? How would you grab this out of your model to compare to the observed data? So in order to do that, I'm going to come back here and I'm going to run the Markoff Cohort extended report. And if we go down to 5 years, which is the beginning of stage 5, and we look right here, the people in the local cancer state are the people who are still progression free. That's our model generated 5-year progression free survival for that strategy. And then the combination of the two, the sum of the two, is the overall survival. So just summarizing that right here, here's our progression free that our model generates. Here's our post progression that our model generates for a total overall survival of 0.84543. But it's too high because our observed data is showing that these are what we should expect. So that's the calibration problem that we're looking at. Our model is generating progression-free and overall survival that's too high because we actually have data to compare it to, and we realize that we've got a small error in the model. I'm just going to check for questions and see if there's any questions. Okay, no questions so far. So in order to move forward with the calibration, what we have to do is we have to instrument the model a little bit prior to calibration to actually generate these two values as independent outputs of our model. Now that's not difficult, but it needs to be done. So let me show you how that was done in this model. So if I go back to the model and I look in tree preferences, you'll see there are actually 7 enabled payoffs in the model. Now the first 2 are cost effectiveness, but the other ones are, I've got a couple of counts in here, 3 counts, and then I use payoffs 6 and 7 to measure progression-free and overall survival at 5 years. So that's specifically what these outcomes from the model generate. So this is the tree preference, just setting them up to be collected. When I go into the actual model and I look at in terms of how we generate the formulas to collect that, and I go to the Markoff info. Now this is your cost and effectiveness primary, but if I go down to the additional sets and scroll down a little bit, you'll see down here it's basically saying if the stage is 5, that means we're 5 years to the future in this annual model. Then by multiply by 1 is just tell me the percentage right now that's in this state. So this is the percentage of the people in the local cancer state 5 years in the future. And because local cancer is both progression-free and alive, that accounts for both of them, or that gets added to both of these two measures. Whereas with the metastases state, that is not progression-free, it's just overall, so it only contributes to the main, to the overall survival. So now these are independent functions of the model. So if I just run the model, run the rankings, and I scroll out here, I can see this model is actually generating independent outcomes for progression-free survival and overall survival for each of the 2 strategies. So that's the first step is once you have your calibration kind of what you want to compare, you have to instrument the model to make sure that's an independent output, that I don't have to sift that out of the existing aggregation of output data. So I've got my payoff set up for the comparison. I can see they're too high, and now I'm ready to run the calibration. So let's move on to that. And you'll see this new calibration view. Now, it probably won't be open for you when you first open TreeAge Pro. So if I wanted to open it, I would just go to the views list and open calibration. And now it's here. And you'll see there's 4 tabs, and they're all important. And let's kind of walk through and see how that's done. So the first thing is the setup. And let me just drag this up so you can see everything. And the analysis type, right? Is this a cohort model or a microsimulation model? Well, it happens to be a cohort model. If it were a microsimulation, I would say I'd change it to this. Now, a little bit of a, and it would run a simulation. Now, a little bit of warning on this. Microsimulation has some noise in it, right? You're not getting exactly the same results every time. So you may need a lot of patience to settle the value. Now, that may be too many, let's say 1 million. You may need a lot of patience to actually get those results from each simulation to be kind of stable. And those means aren't kind of reflecting a lot of noise related to the stochasticity of the analysis. So simulation runs in general, but calibration in particular can take a much longer time. So that's why we're not going to try to do that today. So we're just to do it as a cohort model. There's two algorithms. Nelder-Mead, that's what quite well known and used widely. I personally prefer the Bobby QA because it has a less of a tendency to kind of fall into a local minimum and gives a chance to kind of move out of that and find the actual overall minimum. So this has some advantages over Nelder-Mead, but there's really just two choices, and it's fine to run either one. My optimization goal here is to minimize the error function. That's most likely what you'll do. I'm basically going to be comparing my model generated values to my observed values, and I want the error between those to be minimized. So you'll most likely be doing this. If it were a different kind of optimization problem, like you were trying to maximize profits for a business, then you might use this maximize. Just checking to see a question. Question for microsimulation, if you fix the seed without reduced noise, yes, I do believe that would help, but it doesn't completely eliminate the problem of kind of overall noise in the simulation. So I would turn it on, but it doesn't eliminate the problem completely. Okay. So now moving on to the next. Down here, these optimization thresholds. So this is how close. This is how close does it need to be before you say it's good enough? And this is, am I still making progress? Like, am I improving as I move through this? So you could set these thresholds to different levels, and that's 1 times e to the negative sixth, or 1 times 10 to the e to the negative sixth. So it's a really small threshold, but they should be small. And you can adjust these if your calibration is not getting close enough, and it's not running enough analyses to get close enough to your targets. So these maybe take a little trial and error to work with, but I've got them set at an appropriate level for this analysis. And this is just a number of max calculations. Maybe you don't want this to run forever. So try 1,000 times. If it doesn't get close enough, just stop. And maybe I need to change some things other than that. So that's your setup. Now moving on to the next one, this is the inputs. So really this is just references to the input parameters, these 4 probabilities here. And these are the values that I want the calibration process to be able to change. And I have them set equal to the original estimates that I generated in the model, right? These are the same as these. This initial step is how much should they change kind of at the beginning of the calibration. And again, it takes a little trial and error to get these to be at the appropriate level, but I'm basically saying adjust them initially by 0.5 percentage point. And then the calibration will start to make those steps smaller and smaller as it gets closer to its goal. And here's my bounds. Basically, what I'm saying here is, okay, I've estimated this 15%. It's unreasonable to use a value less than 13 or higher than 17%. So I'm basically setting bounds that say don't let the calibration kind of run wild and take these values into unreasonable value, or take these inputs to unreasonable values. So those are your inputs. The next step is to move on to the targets. And these targets are the things related to the 5-year progression-free and overall survival, right? So I had already instrumented, like we talked about a few minutes ago, the 2 payoffs 6 and 7, to represent progression-free and overall survival. Plus, I need the strategy, right? So this is treatment 1 PFS, treatment 1 OS, treatment 2 PFS, treatment 2 OS, and these are the target values that I had. This would be from observed data. Back when I was illustrating the problem, I'd only looked at the treatment 1, but I'm also calibrating treatment 2. So I had observed data for both, and I've put it in here. And these values are lower than what the model is currently generating, right? The model is currently generating 41.7%, 8.45, 44.2%, and 8.51. But in my observed data, these numbers are lower than that. Not significantly lower, but a little bit lower. And then this is the Goodnessoffit function. And you don't have to change this. It just gives you the ability to get very fancy with it if you want to play with this. Simple square, sum of square differences always weights them all the same. But if I change it to expanded, then I could change these weights to say this one's more important. I'm more certain that this observed data is this observed value is really good, so I want to weight it more. I want to say anything that deviates from this should be considered a bigger problem than deviates from this. I'm not going to do that. I'm going to use the simple sum of square differences, but that's when you would use the weight, is by changing that. I see there's a question, but a good time to take more questions. If you want a likelihood, this is a question. If you want a likelihood-based GOF, could you enter that in expression? Yes, there's a custom expression, and you could put whatever you want in here. Now, you better know what you're doing, right? Like, this wasn't generated randomly. This is generated based on the simple sum of squares. So, but if you wanted to get fancy and get, really, really specific about how you want to optimize, then you would put that expression right here. Okay, so that's it for the, no, I don't want to do that. I'm going to go back to simple, and we're ready to move on to the next one. Finally, we're on results, and results won't have anything until I run it. So let's run it. And I'm going to click this run, and now you see it's running the model. And see, this Goodnessoffit is getting smaller and smaller, which is better and better because we want it minimized. So what happened? Well, we started with our original calculation. And let me minimize this so we can see more. And out here, we see the values are generated by the model and the differences between what the model's calculating and what we were targeting, right? So here's our original values, inputs, here's our original outputs, and this is how far they're off. And slowly but surely, the calibration process is adjusting those inputs. Notice the step here, right? 15 plus the 0.005, right? Adjusting these and getting better and better results, and this error function is getting smaller. That doesn't mean it gets consistently smaller. Like, it's going to try some value that was worse and say, oh, that was worse, let me go back the other direction, right? So it's iterating its way through different calculations and trying to get to the point, or eventually reaching the point where the tolerance was good enough, the Goodnessoffit was small enough in this case, that we consider that good enough and it's time to stop analyzing. And if I run it again, because it ran fast, you'll see that the best analysis so far, the closest, is always in green. And that moves as it finds a better one. And when it got down to 102, it said, okay, not only is this 102 the best one, but it's within tolerance. I don't need to do any more calculations. So the calibration is complete. Now let's look at what we found, what it found. Well, what we expected, or what we observed, was that the 5-year survival, progression-free and overall, was too high in each of the 4 cases. Progression-free, overall, each of the 2 strategies. I was expecting, partly because I've done this many times on this model, is that the progression and death is too slow, so the progression probabilities and potentially the death probabilities, but definitely progression, should increase. And what did we see? It did increase. Our original value was 0.15. Well, now it's 0.1514. And this was 14%, and now it's 0.1412, right? So it did, the calibration process did, in fact, increase those probabilities as we expected, and increased this probability as well, which was originally 1%, but it actually reduced this one. It's compensating for these rising. This one reduced a little bit, from 10% down to 9.2%. And what did that do to our outputs? We got our error almost to 0. And now our results coming out of the model are extremely close to the observed data that we saw in the original kind of, let's say, clinical trial data set, or wherever that data came from. Let me see, there's some questions here. Can you expect to export the GOF graph? I'm not totally sure. I know you can save it as a, I haven't tried that. I know you can save it as a independent output that can be generated here. I don't remember whether you can export this graph. You definitely can export this data here, and you could regenerate the graph. I'm not sure exactly how many exports we have. I have to look at that later. So in essence, kind of in conclusion, what we've done here is we had the model. Our conclusion is actually here. Let me go back up here. Our observed data our model data from the original model was too high. The survival percentages were too high. So we expected to increase the progression probabilities, and sure enough, it did increase the progression probabilities which is exactly what we should have expected. Now, at this point, what we can do is say, you know what? I like these new progression probabilities. Let me put them in the model. So if I click this button, then it will change these values in the model. So I could just click the button and now we have new probabilities. So we're taking the word of the calibration as being better than what we had before. I could also use it as inputs for a new calibration. So if I wanted to run a calibration again, let's say with a different algorithm or something like that, it's now using the best values it found so far as the basis for the next calibration. So if you wanted to do kind of a series of calibrations to kind of refine it and refine it and refine it again. So I think that's all I have for you today. But in essence, hopefully you've seen the full kind of picture from beginning to end, which is I've got a model, it's generating results, I have some observed data, and it's not matching. How can I use that data that I do have to calibrate the model and make my model more accurate? And now I can have a little bit more confidence, but quite a bit more confidence in the things like the ICERs and the net monetary benefits that I'm using to draw conclusions about the strategy than I could before. And because I put my calibration data back in here, if I now run the model, now I'm getting the data that matches here. And now I presumably have a more accurate ICER that I can use to compare strategies because I'm more confident that my model is better representing reality. And that's all I have to have for you for today. But I'm going to go take some questions. Let's see. Go back here. Would this work for non-fixed transition probabilities? Yes, absolutely. You could. It would be very difficult to do it on a table. If you had a table of data that was kind of manually entered at different times, then you might have to kind of adjust the whole table up and down rather than individual values. So that would be a little bit trickier. But with a parametric distribution, you would have something like a Weibull distribution, right? So you have a distribution here. Let's say it's a Weibull. And these could be variables right here. Instead of having fixed numbers here and here, you could have variables here, and those variables could be part of your calibration process where they could be adjusted down, which would change the Weibull distribution. And then that Weibull distribution itself might be used using, let's say, the distrans_prob function to calculate transition probabilities, or it could be being used in a DES model, or it could be being used in a Part-SA model or something like that. But yes, you could definitely do that. Another question was, is there a reference for the first algorithm in the documentation? I don't think we have a lot of documentation on that, the Bobby QA. I have to look at that. David, if you want to, pretty sure that's David Neymark. If you want to discuss that afterwards, I'll see what we can find on that algorithm. Any further questions about what we did today with the calibration? Okay, well, I guess that means we're done. So first of all, I want to thank you all for joining me today. I hope you'll try out the function and see how it works. And by the way, not only did we use this example model that you'll see in the in the help file, excuse me, in the files, the example models, we also use that same model in the help. So if you go to that chapter on calibration, it kind of walks through all these things I did today, more at your own pace because you can read through. So we try to use the same consistent example to make it easy kind of to follow from, help to webinars, etc. So I think that will be useful. Vanessa, thank you for that. Just remember, you need to update your software to TreeAge Pro 2020 to use this function. You probably can just go help update to update your software. But if you need any help with updating your software, please don't hesitate to contact us at support@treeage.com and we'll provide assistance. So unless there's any more questions, I'm going to close the session, but I appreciate all your time and hope you enjoy the new feature. Thank you.